Welcome and thank you for joining. Let's take a look at a trig equation. This time we are solving a question from the textbook. I think is on page 437, number 20. It was assigned for homework. So let's read the question first. We have root 2 sine theta equals square root of 3 minus cosine theta. So we have three terms in this equation. We have a sine term on the left, a constant term, and a cosine term on the right side of the equation. We are solving in the domain of theta between 0 and 2 pi. Whenever solving trig equations, we prefer to have the same trig ratio used throughout the equation, and that's not the case in here. So our goal would be to combine the terms in such a way that we can create an equation that contains either sine or either cosine, so not both of them. Now, if we didn't have this square root of 3, this constant term, this could have been very easy. Just dividing by cosine theta both sides could give us tan theta on one side and a constant here. But we have a constant term in here, which makes things a little bit more complicated. So one of the strategies that we can use is to replace the sine of theta with something that contains cos theta. And when you think really hard about it, there is no really a formula that connects sine with cosine theta. So, but there is a connection that exists between sine squared and cosine squared. So remember, sine squared theta and cos squared theta join each other to give just one. That's a Pythagorean identity. So what we're going to try to do here is bring sine squared and cos squared to this equation. And we know that since in an equation we can transform it by applying the same transformations to both sides. We create an equation that has the same solutions. So in this case, it would be helpful to bring both sides of the equation to the power of 2. And that's what we're going to do now. So we're going to bring the left side to the power of 2 and the right side to the power of 2. So now we'll apply the power, so a little bit of algebra. So root of 2 to the power of 2 would give just 2. And sine theta to the power of 2 would be sine squared theta. And that would equal root of 3 to the power of 2. Remember, this is the a minus b squared expansion. So that would be a squared, so root 3 squared or 3. And then minus twice ab plus b squared. Now remember, twice, this is our a, this is our b. So 2 root 3 cos theta. And lastly, we have plus b squared or plus cosine squared theta. Now, we brought kind of a new problem in here, so we do have cosines still on the left, but we still have sine squared. We do know why we are doing this, right? So we are replacing sine squared by 1 minus cosine squared theta, so the Pythagorean identity, equals 3 minus 2 square root 3 cosine theta plus cosine squared theta. So next we have to expand and simplify, see what this turns into. So we have to expand number 2, multiplying 1 and cos squared theta. Okay, it looks like a longer, bigger equation, but at least we have the same variable throughout the equation, the cosine theta. So we're going to bring these terms to the left side because we notice that we have ended up with quadratic equation. And we're going to do this for every term, so the negative 2 root 3 becomes positive, positive cos squared becomes negative, and on the right side of it, we're going to leave 0. So it's a second degree equation, right? Now, let's combine the like terms. So let's see what is alike and what it's not. We have cosine squared terms. We have negative 2 cosine squared and negative 1 cosine squared, and together they will make a negative 3 cosine squared theta. Now we also have these two little constants that can combine together. But before we write the constants, we're going to write the first degree term, which is 2 root 3 cosine theta. And lastly, we have 2 minus 3, which is minus 1 equals 0. Now we are solving a quadratic equation. Obviously, trying factoring here can be a little bit difficult because we have a radical coefficient. So what we're going to do is use the quadratic formula. And before I use the quadratic formula, I prefer to have positive leading coefficient. It's not a must, but it's always helpful. It makes solving the problem a little bit more natural, or feel natural at least. And here we go. We are multiplying, or you can think of it as division, by -1 every term in the equation, and we obtain 3 cosine squared minus 2 root 3 cosine plus 1 equals 0. So quadratic formula, here we come. So cosine of theta, which is our unknown, would be equal to, remember that quadratic formula is -b plus minus square root b squared minus 4ac divided by 2a. Oops, let's extend this root. Now, cosine theta will be negative. Remember the value of b is -2 root 3. And then plus or minus the square root of b squared, this is our b value, so we're going to bring it to the power of 2, and then minus 4 times a, our a value is 3, times c, and our c value is 1. All of it will be divided by 2 times a, so 2 times 3. So let's see what we have cooked here. We have cosine theta equals, so these two minuses will make a plus, so 2 root 3, plus and minus, square root. Now, -2 root 3 to the power of 2 will be -2 squared, or a 4, times root 3 squared, which is 3. So 4 times 3 is 12. -4 times 3 times 1 is also 12. This looks very, very interesting. And now we are dividing it by 6. So as you can see, the discriminant ended up being 0. That's usually good news. So we have 2 root 3 over 6. And if you simplify this, it would be equal to root 3 over 3. So we are getting very close to our solution. We only got one ratio for cosine theta. And we're going to find the angle theta just like we always do when we're given the ratio, using the inverse of the ratio used. In our case, cosine, root 3 over 3. This is not a special ratio, by the way. So it's not root 3 over 2. It does look like it, though, but it's not. So in radians, it will give us 0.955 radians. Now, remember how we find the angles within a specific domain. First, we get an angle from the calculator. We got this. Next, we draw. So remember, calculator, draw. Now, here is my little Cartesian plane. I'm going to draw the angle I just got in here is almost 1 radian, so almost 60 degrees. So I made it, look like it, but I'm pretty sure it's not exactly 0.955 radians. Now remember that there is more than one angle that has the cosine ratio of root 3 over 3 within one period, or within 2 pi. And when using cosine, remember that we create the other angle by reflecting the terminal arm about the x-axis. So the other solution will be right here, which makes it 2 pi subtract 0.955. So here we go. We're going to get the other angle, which is 2.185 radians. Give me 1 second here. So I have to double check this. So 2 pi would be 2 times pi. I'm trying to calculate this. 0.955. Okay, 5.33 radians. I knew something was wrong with this. We fixed it on time. There we go. So there are two solutions, either 0.955 radians or 5.33 radians. Now, here is a short little story that I'm going to tell you right now. Remember how we came this far? So in order to solve for angle theta, we had to square both sides of the equation. And rightfully so, we said that if you apply the same transformations to both sides of the equation, you create an equation with same solutions. And remember that when we solved equations such as, say, for example, let's say x equals 2. That's an equation, by the way. So if you add a number in here, then you would obtain the same equation, so with the same solutions. If you subtract a number, you would obtain an equation with same solutions. If you multiply x equals 2 by a number, let's say 2x equals 2 times 2, you still get an equation with the same solution. If you divide by a number, you still get an equation with the same solution and so on. However, when we square both sides of an equation, this story is a little bit different. And I'm going to give you a very simple example to perfectly understand this. So say, for example, that we have x equals 2, and that was the solution we got from an equation. If we square both sides of this equation, then we would say that if x equals 2, it makes sense to say that x squared would equal 2 squared. So in a more simplified form, we can say that x squared equals 4. So if you say that x equals 2, then this one here is true as well. But if someone asks you, hey, you have an equation here, can you solve for x from x squared equals 4? And then you would say, sure, I know how to do this. So all I have to do if I have x squared equals 4 is square root both sides of the equation, and oops, wait 1 second, I need to take both plus and minus root of the right side. So, and that will give us x equals plus or minus 2. So that will give us, in other words, not just one, but 2 solutions. So now, where did this second solution come from? Because look at where we started, right? So here is an explanation to it. Whenever we square both sides of an equation, that's what we did in here, we produce new solutions. And that is because when squaring both a number, we can obtain that value by squaring its actual value and the opposite of it. So if you are squaring negative 2, you're going to get, a 4, which comes from a negative 2 or a positive 2. So that is something, or a strategy, that we use to solve the equation, in our case, squaring both sides. And that might lead to producing solutions that are extraneous for our equation. So it is very important that whenever we solve equations, and in the process of it, we use squaring both sides of it. And it doesn't have to be just trig equations, like any equations. If we square both sides of it, then at the end we have to check all the solutions we obtain, because chances are we have created some false or extra solutions. So let's see how this worked out for our equation here. So our equation was, the original equation, root 2 sine theta equals root 3 minus cos theta. So I'll write this down here. So root 2 sine theta equals root 3 minus cos theta, right? It was minus, not plus. Yeah, it was minus. Cool. Now, we're going to test our first solution, 0.955 radians. So what that means is that if you substitute theta by 0.955, so by this answer right here, 0.955, and you do the same thing to the other side, root 3 minus cosine of 0.955, then the left side of this equation will turn into, I'm just doing the calculations here on my calculator. So we have multiplied by sine of 0.955. Remember, your calculator has to be set to radian mode because we are using radians here. And you will see that the answer we get is, for the left side of the equation, 1.15, and then 3/4 in there, which I'm going to leave there because why not? Now, let's do the right side of it. So we have square root of 3 here. And from square root of 3, we are subtracting cosine of 0.955. And I get the same number, actually, 1.15444. So the left side equals the right side when the angle is 0.955 radians, which we're going to say it's a pretty decent solution. Now, we're going to test the other solution, which is 5.33 radians. So let's see what that does to our equation. So root 2 sine of 5.33, we're just going to leave it there, equals square root 3 minus cosine of 5.33. So square root of 2 multiplied by sine of 5.33, that gave me negative 1.15 and 29. Now, the other side, I'm going to make it green because why not? So, negative 1 point. Okay. Negative 1.153. That's the left side. Now, let's do the right side. Square root of 3. Subtract cosine of 5.33. I got 1.15296. So different numbers. So one is positive, the other is negative. So we're going to say that these two values are different. So what does that tell us about this solution? That's an extra solution that we got from squaring both sides, but it's not actually true. So we're going to say that the only solution that we'll accept in this case would be theta equals 0.955 radians. Now, another way to check your solutions is by using Desmos, right? And what we're going to do, the way that I like to use Desmos and the way I like to prove my solutions with Desmos is by writing each side of an equation as a function on its own. And what we're going to do is focus only on the domain between negative pi and positive pi. As you can see, the only point of intersection, or the only point where the left and the right side will meet, is at the angle 0.9555. And voila, this is the solution to this equation. I hope these instructions made sense. Continue practicing. Practice makes perfect, and learning is fun. Bye for now.